To solve the vibrational motion problem, we're going to use a center of mass coordinate system. So what we mean by center of mass is that if we put like a teeter-totter, put a fulcrum at a certain point between the two masses, that when we're at the center of mass, we're at the balance point between the two masses, so that those masses exactly balance and our balance is exactly level. So the center of mass is such that, so we'll call X bar is the center of mass of the system. The X that denotes the center of mass. And at X bar, the mass 1 times the distance to X bar is equal to mass 2 times the distance to X bar for that mass. So notice that D1 is X bar minus X1, and D2 is X2 minus X bar, because I want the positive distance. And since X1 is negative, I have to subtract that from X bar to get this distance here. And since X2 is positive, I subtract that from X bar to get this distance here. So with those definitions, I can show that M1 times X bar minus X1 is equal to M2 times X2 minus X bar. And so this allows me to solve for the center of mass with respect to X1 and X2. Solving for the center of mass gives me that X bar is equal to M1 X1 plus M2 X2 divided by M1 plus M2. In our new coordinate system, we're going to set this center of mass equal to 0. So now, if I look back at my condition for where that center of mass is, and I plug the center of mass being 0 into that, I can show that minus M1 X1 is equal to M2 X2, or M1 X1 plus M2 X2 is equal to 0. So now if I let R, the distance between M1 and M2, equal X2 minus X1, that's going to be my new variable. That gives me a relationship for X1 and X2 with respect to R. So we can see that X1 is equal to X2 minus R, and that X2 is equal to R plus X1. Now I have three equations, 1, 2, 3, in three different variables, X1, X2, and R. So if I eliminate X2 from X1, I find out that X1 is equal to minus M2R over M1 plus M2. And if I eliminate X2 from X1, I find that X2 is equal to M1R over M1 plus M2. So my change of coordinate system involves replacing X1 by minus M2R over M1 plus M2, and X2 by M1R over M1 plus M2. What I'm really interested in, though, is the kinetic energy operator, because I want to know what the total energy is for this system. And I need to know what the kinetic energy is as my molecule vibrates. What's that kinetic energy? And then also what the potential energy is, which I know is 1/2 kr squared. In our X1, X2 coordinate system, we can write the kinetic energy as 1/2 m1 times the velocity of m1 squared, 1/2 m squared, 1/2 mv squared, and recognize that the velocity is just the derivative of x with respect to time. And then I have to add the kinetic energy of my second particle, so plus 1/2 m2 dx2 dt, that quantity squared, so the velocity of mass 2 squared. So this would be in my x1, x2 coordinate system, but I need to replace x1 by our value for x1 in terms of r, and I need to replace x2 by our relationship for x2 in terms of r, so that I get everything in terms of r. So notice that dx1 dt is equal to minus m2 over m1 plus m2 times dr dt, and that dx2 dt is equal to m1 over m1 plus m2 dr dt. So if I plug these in for my derivatives and I do all of the algebra necessary, I find that this is equal to 1/2 m1 times m2 divided by m1 plus m2 times dr dt quantity squared. Now, you might recognize this quantity as the reduced mass. So we give this the symbol mu, and this is called the reduced mass. And so I can write my kinetic energy as 1/2 times the reduced mass times the derivative of r with respect to time squared in this new coordinate system. So notice that to get to this kinetic energy in this new coordinate system, that really we've just replaced the mass with the reduced mass, and x2 minus x1 with r. And so to get to the kinetic energy operator, I'm just going to make the same kind of substitutions. So for each x, the kinetic energy operator is minus h bar over 2m times the second derivative of x. So if I just am replacing m with mu and x with r, my kinetic energy operator for in this new coordinate system is h bar squared over 2 mu d squared dr squared. And so that is the kinetic energy operator that I'm going to use in this new coordinate system in order to solve my Schrödinger equation and find the eigenvalues and eigenvectors for this harmonic oscillator.